All right, hello and welcome to Spacecraft number 113. My name is Nick. I am a student at the University of Arizona in Stewart Observatory. And welcome to Space Drafts. For those of you who are new here, very special welcome to all of you. Space Drafts is Tucson's version of Astronomy on Tap. AOT, as it's abbreviated, is a network of events for sharing astronomy with you, the general public, done in bars and pubs all over the world. So, if you're out somewhere, have a look at Astronomy on Tap. They might have an event somewhere close to where you might be visiting or where you might be from if it's your first time in Tucson. How our show works here is we have two 25-minute talks for you tonight. We'll have a 20-minute intermission in between those talks for you to go in and refresh your drinks. We also have some trivia questions amidst these talks for you to get engaged with our experts here. With those trivia questions, we'll be calling on members of the audience who raise their hands, and whoever answers the trivia questions correctly, you will be awarded a little piece of our merch, which is that at this corner, all the way back there, is our merch table. Speaking of merch, it is available for sale. We only accept cash, unfortunately, so if you don't have your cash and want some merch, come back next month and grab some of that. We also do accept donations. Those help keep this show running, so if you are so inclined, we greatly appreciate any donations. With that, I think that's all my introduction stuff. So, here to talk about what we know and what we don't know about, if I may editorialize a little bit, my favorite in the solar system. Please give a very warm welcome to University of Arizona graduate student Devin Hoover.
All right, just into this. Okay, good. Hello, everyone. I'm Devin Hoover. I'm a third-year PhD student at the University of Arizona Lunar Planetary Laboratory, currently studying Titan's upper atmosphere. And unless I am mistaken, the last Space Drafts presentation about Titan occurred about 8 years ago. That's an awfully long time ago, and there have been some recent developments in Titan research since then. So that needs an update. So today I'm here to present a brief survey of what we know about Titan, as well as some currently unresolved mysteries about Titan. So first of all, what is Titan? Titan is the largest moon orbiting the planet Saturn, and it is the only solar system moon with a dense atmosphere. So here you can see a photo of Titan in front of the planet Saturn, captured by Cassini. It is very pretty. So here is a brief survey, or a brief list of Titan's main properties compared to Earth's. Titan's radius is about 40% that of Earth's, making it the second largest moon in the solar system, with Jupiter's moon Ganymede being slightly larger. Titan orbits Saturn with an orbital period of about 16 days, which is basically equal to its rotation period, implying that Titan is tidally locked to Saturn. This means that the same side of Titan is facing Saturn as it orbits around the planet. Compared to Earth, Titan has much weaker surface gravity, which, combined with a very high surface pressure, as we're going to see later, gives rise to a very thick, vertically extended atmosphere. Both Titan and Earth have also very similar obliquities, or axial tilts, relative to the Sun, meaning that both experience seasons. Finally, both Titan's and Earth's atmospheres are nitrogen-dominated. Titan's much more so than Earth's. So due to these properties, and other ones that we're going to see later, Titan is considered the most Earth-like object in the solar system, of course, besides Earth. What's interesting is that we know from geochemistry that Earth used to have significantly higher levels of methane in its atmosphere than it does today, meaning that Titan more closely resembles the early Earth's atmosphere rather than the present one. This makes Titan an extremely interesting object for astrobiology, planetary habitability, origin of life. So here I'll just present a brief timeline of Titan exploration. Titan was discovered in 1655 by the famous Dutch astronomer, Christian Huygens. You can see his picture there. Fascinated by Galileo's discoveries, Huygens built his own telescopes to make his own observations, and he first discovered Titan using one of those telescopes. Huygens was also the first astronomer to demonstrate that the unusual appearance of Saturn through a telescope was due to the presence of its rings. I think Galileo famously called those features Saturn's ears because he didn't have the resolving power in his telescope. So here you see an image of Saturn and Titan. Titan on the lower right here through an 11-inch backyard telescope. And I can imagine that Huygens might have seen something similar when he was making his first observations of Titan. So I don't exactly know exactly the trivia questions is going to work, so someone might have to help me out here. But here's the first one. In what year was the first evidence for Titan's atmosphere discovered? Tyler, you raise your hand first. That is not correct, sorry. You in the back. I saw your hand first. That is correct. 1908. Yes, okay. I don't know where the prizes are, but you deserve a prize. So that evidence was limb darkening, which is an optical effect, and which if we look at the disk of a distant object like Titan, the center appears brighter than the edge or the limb. And the reason why this works is if we consider these incoming solar photons coming from the sun that pass through Titan's atmosphere, they're more likely to be scattered back by the denser lower atmosphere than at the edges, resulting at in the center appearing brighter. So limb darkening is actually a very easy test to determine if a distant object has an atmosphere. Although if you're into exoplanets, I am aware that this is more commonly associated with stars. But that discovery was kind of obscure. I like it. It was discovered by a Spanish astronomer and not really known outside of that community. But so the next evidence for Titan's atmosphere was the spectroscopic detection of methane by Gerard Kuiper. This is the same Kuiper who is the namesake behind the building in the University of Arizona campus. Basically, if we consider outgoing photons from Titan, they are absorbed by methane at very specific wavelengths, resulting in methane absorption bands if you plot a spectrum. So I believe this is Kepler's actual data, and you can see right here there is a gap where there should be some signal, and that's due to the absorption of, I believe it's infrared light by methane there. I forget the exact wavelength. So the first spacecraft to observe the Saturn system was Pioneer 11 in 1979. And it captured this very grainy image of Titan. However, the Titan was not a main focus for the Pioneer 11 mission, and it didn't necessarily have the right instruments to look at Titan, as we now understand in hindsight. So it was not until the Voyager missions, I believe in 1980 and 1981, that we achieved the very first accurate measurements of the composition, temperature, and structure of Titan's atmosphere. It was actually through the Voyager measurements that we first demonstrated that nitrogen is the main component of Titan's atmosphere. Previously, we actually thought it was methane or possibly molecular hydrogen. I should also note that Titan was a major object of focus for the Voyager 1 mission, so much so that the trajectory was designed to achieve a very close flyby of Titan. At the expense of Voyager 1 not visiting Pluto, so I apologize to all the Pluto fans in the audience. We prioritize Titan over Pluto. But nevertheless, the Voyager data still lacked observations of Titan's surface. The atmosphere was too thick for the Voyager instruments to observe the ground. Today, the bulk of the understanding about Titan comes from the Cassini-Huygens mission. Launched in 1997, Cassini orbited Saturn between 2004 to 2017, after which it plunged into Saturn's atmosphere, never to come out again. Cassini carried a suite of multiple instruments that observed Titan at different wavelengths, which allowed it to make measurements of Titan all the way from the surface to the top of the atmosphere. Cassini also carried a small lander, the Huygens Entry probe over here, which conducted detailed observations of Titan as it descended through the atmosphere to the surface. The idea basically being to calibrate or contextualize the Cassini measurements. So on January 14th, 2005, I believe that's about almost 21 years ago, if I do the math right, the Huygens probe landed on Titan, marking the furthest landing from Earth to date. I'm not going to show it here just due to time constraints, but there's a 4-minute, 40-second video footage from the Huygens lander as it descended through the atmosphere to Titan's surface. I highly encourage you to look it up. I'm pretty sure it's on YouTube somewhere. It has to be. But nonetheless, here is a frame of one of the video during its descent, and it beautifully captures some of the complex landforms on Titan's surface. Looking at this, I see what could be some highlands, some possible rivers or drainage channels, and what could be some plains or possibly a shoreline or something. Very cool. Now, this is an actual, I believe, unedited image of Huygens from Titan's surface. What you see here has been described as either a muddy floodplain or a lake bed, and you can kind of think of it as having a creme brulee texture, according to one Cassini mission scientist. So these rocks here are water ice pebbles that have been coated with hydrocarbons. And it's important to note that the pebbles appear well-rounded, which scientists have interpreted to mean that they've been eroded by fluids on Titan's surface. Now I'm going to survey our sort of current understanding of Titan. It's not going to include everything, but I will touch upon the atmosphere, and then we'll move down to the surface and then the subsurface. So like Earth, Titan's atmosphere is divided into 4 layers, troposphere on the bottom, and then the stratosphere, mesosphere, and thermosphere. So like on Earth, the troposphere in Titan is where most weather occurs. And the stratosphere, there's a unique layer called the organic haze layer, which is analogous to Earth's ozone layer. So on Earth, the stratosphere is warm relative to the troposphere due to the absorption of ultraviolet radiation by ozone. While on Titan, the stratosphere is warm relative to the troposphere due to the absorption of infrared radiation by the organic haze layer. Now, depending on the season, there is also another feature called the detached haze layer that arises in Titan's mesosphere. And in the thermosphere is where organic haze production starts, as we're going to see in the next slide, starting with nitrogen and methane photochemistry. Also note that Titan's atmosphere extends well above 1,000 kilometers. So we're talking about a much more vertically extended atmosphere than Earth's. So since the organic haze is very critical to understanding a lot of processes on the moon Titan, it's important to discuss how it forms. And it starts in the upper atmosphere when you have these solar ultraviolet photons and charged particles from Saturn's magnetosphere. They come in and they dissociate or break up nitrogen and methane. And in some cases, they also ionize them, so they remove electrons. And that triggers a cascade of photochemical reactions that build up these organic molecules. And the organic molecules will continue to react and accumulate into the organic haze. And eventually, you'll get these tiny aerosol particles that will descend to Titan's surface. Titan's organic haze layer is so thick that it contributes to that distinct orange color on Titan that we saw earlier, and that's the reason why we can't see Titan's surface in the visible wavelengths. And given the similarities between the early Earth's atmosphere and Titan's atmosphere, it's possible that this process potentially mimics early Earth's prebiotic chemistry, although we might need a bit more information to understand how that works. And to sort of understand this process of haze formation, scientists have sort of recreated this process in the lab by taking mixtures of simple molecules like methane, nitrogen, carbon dioxide, water vapor, and so on, and radiating them with ultraviolet radiation. And the result is a wide variety of organic molecules that have been sort of collectively called tholins. And they range in color from yellow to black, In this case, we see some solid tholins in this sort of reddish-brown color. Laboratory experiments seem to suggest that tholins can facilitate prebiotic chemistry, meaning that they can provide the raw materials needed for life. However, I should note that the spectral properties of these tholins measured in the lab do not completely match up with what we see from the Cassini data. So something must be missing in our understanding of how Titan's organic haze forms, although we don't know exactly what that is. Nevertheless, there are multiple solar system objects that are thought to contain these tholins, like Europa, Pluto, and Charon. And what I mean by that is the reddish-brown areas in each of these images are thought to be a mixture of tholins. So this one is a kind of two-parter for a trivia question. First, what is Titan's surface temperature? Is it 78 Kelvin, 93 Kelvin, 128 Kelvin, or 273 Kelvin? And oh yeah, in the back. You might go with A. It is not A. It is very cold, but it's not A. Yeah, you in the back. B. It is B. Yes, it is 93 Kelvin. Next, what is Titan's surface pressure? In the front, yeah. D. It is not D. Yes, you, sir. It is not B. 2 options left. 50-50 shot, guys. Sure. Yeah. It is not A. Everyone else shout out the answer. It is C. So I asked these questions because the temperature and pressure are very close to the triple point of methane. And in chemistry, the triple point is the temperature and pressure where a substance can coexist simultaneously as a solid, liquid, and gas. This gives rise to Titan's hydrocarbon cycle, which is a hydrological system analogous to Earth's water cycle. And basically, it involves the evaporation, precipitation, and condensation of methane, and to a lesser extent, ethane. So we do get methane clouds, we do get methane rain, and methane runoff, which is pretty cool. And it plays a critical role in shaping Titan's surface features. There is, however, one notable difference between the hydrocarbon cycle on methane, or on Titan, and the water cycle on Earth. And that is that on Titan, methane can be transported up to the upper atmosphere, where it can be broken up and it can also escape to space. So Cassini radar data have revealed several lakes, seas, and rivers on Titan that are mostly composed of liquid methane and ethane as sort of a byproduct of this hydrocarbon cycle. For example, this is a radar image, I believe, of Lake Mare, which is a really huge lake in Titan's northern hemisphere. Through thanks to repeated observations from Cassini, scientists have been able to observe evolving features in the lakes, most notably the shoreline. But there is one feature that has kind of stumped scientists so far, and that are these magic islands. So here is the bottom, whoops, the bottom right, well, image on the bottom right, because I can't click the laser pointer, that shows the evolution of a magic island over time. And no one is quite sure what it is. People have hypothesized that it's waves, bubbles, subsurface ice that has risen to the surface, or sort of silt-like material that is that's suspended in the lake. So this is ongoing area of research. Cassini radar data has also detected dunes on Titan, which are confined to Titan's equatorial region. So here is an image of the Bellet Sand Sea, which is a really huge dune feature on Titan. If you note the scale, I believe that's 50 kilometers in the scale bar. So on Titan, most dunes are longitudinal, meaning that the direction of the dunes is parallel to the direction of the prevailing wind. And interestingly, this is quite rare on Earth. We believe that the sand on Titan's dunes is composed of those descending aerosols that are generated in the upper atmosphere, and they descend to the surface. So on average, these dunes are 1 to 2 kilometers wide, hundreds of kilometers long, and about 100 meters high, which would make them significantly larger than Earth's dune fields. Cassini radar data has also revealed that Titan has relatively few impact craters compared to other solar system objects. We believe this is due to active geologic processes that sort of reshape Titan's surface. It can possibly tear up the entire surface or bury impact craters in the organic material. But impact craters have been suggested as potential sites of prebiotic chemistry, which make them absolutely fascinating. So it could be possible that if you imagine a giant asteroid or meteorite coming in and colliding with Titan to make these craters, there could have been enough energy to melt the organic material and the water ice that we expect the craters to have. And it is possible that while this happens, the liquid water, as a result of that melting, mixes with the organic material and possibly gives rise to biomolecules like amino acids or sugars or lipids or something like that. However, the precise composition of these impact craters is not well understood yet, so it is still very hypothetical. So we don't have a lot of constraints right now about Titan's interior structure below the surface. But we do have some indications from early Cassini gravity data and radio tracking measurements. And an early analysis seemed to suggest that Titan's surface is an ice shell, and below that is a global liquid water subsurface ocean, which would make Titan an ocean world. However, this has been challenged by a recent reanalysis of the same data, and by recent I mean a paper published in Nature about a month ago, where they took the same data and used new and improved techniques. And what they found that better fits the data is that beneath Titan's surface lies a series of high-pressure ices that might contain pockets of liquid water that those authors believe still could be transported to Titan's surface. So Cassini has really revealed a lot about Titan, but there are some major mysteries that remain unexplained, and there is an exciting future of Titan exploration that I also will briefly cover. So I have 3 questions that I think are the most important in future Titan research. The first are, what are the main sources and sinks of methane from Titan's surface? So to really understand this, we have to go back to the dissociation or breakup of methane in the upper atmosphere. That sort of kicks off the organic haze production. When this happens, it produces atomic and molecular hydrogen as byproducts. And those particles are so light that they can just escape Titan's atmosphere. And note that once they do, they can be recombined to form methane, so that would make the breakup of methane irreversible. It has been calculated that due to this process, if there was no replenishment source for methane, it would take approximately 15 million years for Titan's current atmospheric reservoir of methane to be depleted. But we know that Titan is much older than that, so there has to be some replenishing source of methane. From Cassini and Huygens, we know that the dunes, lakes, and seas do have some methane reservoirs that they contribute to the atmosphere. But if you do the calculations, you realize that it's actually not enough to replenish the methane that is broken up and also escaping. As a side note, the rate of escape from the top of the atmosphere for methane is still hotly debated among Cassini scientists. But anyway, all this is to say, there is an unknown source of methane from the surface that awaits future discovery. Some potential hypotheses include like a methane subsurface table, analogous to like Earth's water table. Or another hypothesis is that you have ethane rain that sort of swaps the place of liquid methane on Titan's surface. But it is still currently unknown. Next, what is Titan's surface age? On most solar system bodies, this can be determined remotely through what is called crater counting techniques. And the basic principle behind it is the older the surface, the more craters you expect there to be. There have been previous observations of craters and dunes on Titan that suggest surface ages between 100 million and 1 billion years. But this is not without its challenges on Titan. One of which being what I talked about earlier, that active geologic processes can sort of reshape Titan's surface. And when it comes to trying to figure out how old it is, it makes Titan's surface appear younger than it actually is. Another sort of bias is that Titan's atmosphere will prevent small diameter craters forming, as if you have really tiny asteroids and meteorites, they just burn up in Titan's atmosphere. We also don't have that much craters to do these sort of crater counting techniques like we can on other bodies. And also the crater density on Titan's surface is non-uniform. For some reason, most impact craters on Titan are sort of abundant in this bright region on the photo there called Xanadu Regio, and not exactly present in large quantities at high latitudes for reasons we don't understand. When we answer this question about Titan's surface age, we should be able to help reconstruct the geologic past of Titan. And finally, is the most important question, in my opinion, is prebiotic chemistry occurring on Titan's surface? Because this can go a real long ways to addressing origin of life research. So we've already seen that Titan's atmospheric composition is very similar to Earth's, and that very complex hydrocarbons are produced in Titan's atmosphere that descend to the surface. So you would think that prebiotic chemistry is possible, but there are a few obstacles to that occurring on Titan. I did show water ice pebbles on Titan earlier, but there's actually not a lot of oxygen-bearing molecules on Titan's surface that prevent biomolecules like amino acids, lipids, sugars, etc., from forming like on Earth. However, it has been suggested that ammono analogs, or NH, nitrogen bonded to a hydrogen, have similar chemical properties to oxygen, so they could replace them, which would result in a completely different biochemical pathway on Titan. There are also features on Titan that had been hypothesized to be cryovolcanoes, like ice volcanoes, that would bring up water to the surface. Although no cryovolcanoes have been concretely identified on Titan. And as I mentioned before, if you wanted to look for prebiotic chemistry, one of the best places to look for that are impact craters. So there are a lot of options to sort of address that question. So now moving on to some sort of current and future exploration of Titan. The James Webb Space Telescope has observed Titan several times since the Cassini mission to track changes on the moon since the Cassini mission ended. So this image here, you see a near-infrared image of Titan captured by James Webb, and that right image is a near-infrared image captured by the Keck 2 ground-based telescope. That's right. And they are 2 days apart. And you can see that the shape and extent of the clouds have changed significantly, which would allow us to track circulation patterns on Titan. In addition, James Webb has also detected for the first time the methyl radical, which is CH3, so like methane with a hydrogen removed. And methane radical is a free radical, so it's highly reactive. And that sort of represents the first step in the organic haze formation process. So also sort of constrain how much of the organic haze is forming at any one time. Looking forward to the future, NASA has selected as the 4th New Frontiers mission, Dragonfly, which plans to send an octocopter to the surface of Titan to investigate questions related to the origin of life, as well as tackle that methane problem that I talked about earlier. The proposed landing site will be the Shangri-La Dune Fields, and then Dragonfly is going to hop along the surface and eventually end up at the perimeter of the Selk crater, whose images you can see there. The idea is Dragonfly is going to sample as many diverse environments as possible over the shortest distance possible. And at each site along the way, Dragonfly is going to sample Titan's surface to look for elements associated with life, as well as some complex biomolecules like amino acids, lipids, and sugars. And it's also going to measure the humidity, temperature, and composition of the atmosphere just above Titan's surface. So it's going to be like a Huygens measurement at every landing site, basically. So Dragonfly is expected to launch in 2028, and it's expected to arrive at Titan by 2034. And I don't believe the presidential budget cuts impact Dragonfly, so I believe this will be going ahead unimpeded. So I'd like to thank you for listening, and hopefully I've convinced you that Titan is a very extremely interesting moon with a lot of applications to habitability and the origin of life. I'd like to thank the Space Drafts team for hosting me, and I'll now take some questions this time. Thank you. So is it usual? Okay. So the question is the fact that Titan is tidally locked usual in the solar system? And I do believe that there are other examples. I think Charon is tidally locked to Pluto. That's the first thing that comes to mind. As far as some other examples, that is escaping my mind, but I have no doubt that there are probably other moons like that. And the second question was, does it have consequences for observations? I don't believe it has any necessary consequences for the observations part, especially as I do believe that Titan has enough winds to transport material from the day side to the night side. I'll have to look into that for more information. Yeah.
Is Dragonfly's going to have a microphone on it?
Is Dragonfly gonna have a microphone on it? I think so. I know that Dragonfly will have a seismograph, I believe, that will really help in understanding Titan's interior structure. As far as microphone, I think that the seismograph might also double as picking up acoustics. But I do atmosphere, so that's not exactly my expertise. Yeah. Lakes of methane and ethane mostly. We believe that, yes. So the biggest evidence before the reannouncement. What?
Repeat the question.
Oh yes, right. So how did people find out that there was water under the surface of Titan? Right? Yes. Okay. So the biggest evidence before that reanalysis was the detection of a Schumann resonance on Titan. So what is that? You can kind of think of it as like a planetary heartbeat, or actually a drum beat, with sort of the top of the drum being Titan's ionosphere. You would have energetic particles from Saturn's magnetosphere sort of interacting with the ionosphere, producing radio waves. And sort of the bottom of the drum, you can think of as Titan's subsurface ocean. And as the radio waves bounce off of the subsurface ocean and are detected by Cassini, that provided the indications of the Schumann resonance. The recent reanalysis realized that the sort of signature of a Schumann resonance was actually not as strong as was originally thought. So that's why they suggested the pockets of liquid water. Another reason why we might expect water to exist on Titan is it formed past the snow line. So basically, if you're in the early solar system, the snow line is the region beyond which water can sort of condense from a gas to a solid. So we'd expect Titan in its early history to accrete ices like water. So that was a very long answer. Okay. Yes, you, sir.
Will there be an orbiter that goes along with Dragonfly?
Will there be an orbiter that goes on with Dragonfly? So right now is just the octocopter that is being proposed. So I don't think so. Yeah. Okay, Tyler. I believe that there's going to be very specific radio frequencies that the octocopter is going to emit that can pass through Titan's atmosphere. But luckily we have the Deep Space Network for that.
All right, so with that, we are going to go to intermission. It is currently 8:06, so we'll be back here, let's call it 8:25. Please go in, refresh your drinks, grab some tacos while they're out. I think they usually close around 8:30. Yeah, so see you back here at 8:06, 8:26. Welcome back to Space Drafts. So our second talk today is being presented by another U of A graduate student here to talk about making mechanical eyes that look at the sky. Please welcome U of A graduate student.
Hey everyone, thanks for coming out to Space Drafts. My name is Brock Parker. I am a third-year graduate student at the University of Arizona Stewart Observatory, and today I'm going to be telling you about the history of optical visible light detectors for cameras. So before I get into this, I want to first present you with a brief timeline of what we're going to be talking about today. And so up on the top here, you can see all of the different devices and inventions that we're going to be talking about. And on the bottom, a few notable events relating to astronomical photographs. So to start with, from the invention of the telescope, originally there was only one detector, and that is your eye. Now, unfortunately, your eye has lots of drawbacks. One of these is that it operates on a short exposure time. And so this means that we can only see the brightest objects in the night sky. And so the fainter objects are hidden from our eyes. Additionally, your eyes follow a logarithmic response to light, meaning that making comparisons between objects of different brightness is difficult because objects that are twice as bright in the night sky do not appear twice as bright to the naked eye. And also, of course, your eye is attached to this imperfect recording device, which is your brain. Memories are historically not great, and so doing comparisons without having any way of actually recording what you see becomes difficult. And this is a photo of Lowell up on Lowell Observatory in Flagstaff. Now, there was, of course, the option that you could draw what you were seeing. And so here are a few astronomical sketches. This is the Andromeda Nebula. Now we know it's the Andromeda Galaxy and the Whirlpool Galaxy. If any of you have actually seen these objects, however, you'll realize that these are not great sketches. They don't quite look like this. And so obviously, drawing what you are seeing is highly subject to your artistic ability, as well as how well you are able to actually see the object in the night sky through your telescope. Despite this, however, there were tons of discoveries done by eyepiece, including the discovery of Uranus, Neptune, all the major planets, moons around Jupiter, Halley's Comets, all of the Messier catalog, and many others. And so here you can see a page from Galileo's notebook detailing the orbit of the moons around Jupiter. So before we get into actually taking pictures, I want to first ask, how long was it between the invention of the telescope and the first astronomical photos? That is correct. It was about 250 years between when the telescope was invented and we first started taking pictures with telescopes. So, to start, let's talk about the invention of the photograph. So this was done in 1822 by Joseph Niepce using a method called heliograph photography. And so what they would do is coat this sheet in a light hardening bitumen. And so what that means is that when light strikes this, the material hardens, and the more light you get, the more material hardens, creating a negative of what you are observing. You can then etch away all of the uncured bitumen with an acid and wash it off, and then shine light through it to get images like this. And so this is the oldest known surviving photograph. Now, it actually took quite a while from when the photograph was invented to when they first started putting it on telescopes. And this was because the original photographs, the heliographs, took hours and hours of exposure time, even in the daylight. And so obviously for faint astronomical objects, this was impossible to use. However, by 1840, the daguerreotype had been invented, which was both much more sensitive and much easier to do. And so in 1840, John Draper took the first known astronomical photograph of the moon, if you will believe that. Now, later that year, he did improve his methodology quite a bit. And so you can see an actual picture of the moon, seeing some of the mirror and other features on the moon. And then this is him with his camera set up on the back of the telescope. Now, in most of the history of observing, the photograph evolved into what we know now as photographic plates. And so these were, instead of being metal plates or like film, we would put them on glass plates coated in a silver gelatin. And so this is very similar to the bitumen, where there is this light-sensitive silver halides that are suspended in this gelatin. And as the light strikes them, this material hardens. and you can then etch away all of the extra material with this photographic fixer, and then wash away everything with a water bath. And then what you get is images like this, where the light areas are dark with more material, and then the dim areas become light. You get a negative of your image. Now, photographic plates suffered from several issues. Obviously, these are better than your eye, but they are still nonlinear because of the way that the interaction of the light with the chemicals and the hardening all worked. You had a nonlinear response to the amount of light that was falling, meaning that objects that were twice as bright, again, did not appear twice as dark on this plate. Also, they had a very low dynamic range. You needed enough light to actually start hardening the material, but you only had a limited amount of material on these plates, and so once you reached all of that being hardened, you couldn't record any more information. The images became oversaturated. And even within this low dynamic range, they only detected very little amount of the light. Less than 1% of the light that actually hit them was captured in these images. And outside of this small dynamic range, essentially none of the light was captured. And so there were lots of photons that were being gone to waste and not captured by these images. Now, there were also lots of discoveries done by photographic plates. They existed for several years. Down here at the bottom, you can see a timeline. And one of the more famous discoveries was the expansion of the universe. So in 1923, Edwin Hubble took this image. This is a photographic plate of the Andromeda, again, nebula, now we know as galaxy. And you can see up here where he wrote var for variable, discovering the first Cepheid variable outside of our galaxy. And this then let them get the distance to other galaxies, and hence the building of the distance ladder and the later discovery of the expansion of the universe. I also want to go ahead and share, these are more recent images using photographic plates. This was in 1973 of the Ring Nebula. And this was done at our very own Kip Peak on the 2.1 meter. So here you can see the Ring Nebula in 4 different wavelength filters. And of course, you can greatly see the improvement from these versus the photos of the moon from earlier. The next big advancement for astronomical detectors was the invention of the photoelectric sensor. So in 1889, the photoelectric effect was first discovered, first documented. This is notably before Einstein wrote his paper on the photoelectric effect, for which he later got his Nobel Prize. This was by Julius Elster and Hans Geidel, and they set up a alkali photocell, which essentially consisted of a metal with a low ionization energy hooked up to some kind of current measuring device. And so as the photons of light struck this alkali, they would ionize the electrons, they would kick it off of the metal, and then with enough electrons, you could measure the current produced. And so what this gave you was, for the first time, a way to quantitatively measure the amount of light from a star. Importantly, however, this was just a single pixel sensor. So you can see one of the first photometers up here that had attached to this small little telescope. So you couldn't get images with this per se, but you could get actual values. And that would let you do things like measure the variation of a star. And so in 1908, Henrietta Leavitt discovered the first Cepheid variable. And so you can see here, these, well, maybe not, these black data points are the actual measurements from the photometer with this light grid overlaid. This isn't really something you could do with a photographic plate because you didn't have a good way to compare the brightness between photographic plates. And even if you did, again, it was nonlinear, whereas this photoelectric sensor is now linear. While we talk about photometers, another important advancement was the photomultiplier tube. One of the biggest downsides to the photometer was that you needed still quite a bright source to produce a large enough current to actually measure. Our ability to measure small currents, in the 1900s was quite limited. And so what the photomultiplier tube did, which was invented in 1935 by Harley Ames and Bernard Salzburg, was take this incoming electron or light and amplify it by many, many orders of magnitude. And so the way this worked is that your electron would come in from the front. You would then accelerate it with a very strong electric field into one of these little diodes. When it hit this diode, you would undergo secondary emission, where the one electron would have enough energy to ionize several electrons. And then these several electrons would be accelerated to the next diode, where they would then again each produce several more electrons. And before you know it, you go from 1 electron to 10 to 100 to up to tens of millions at the output. And now you have a signal that you can actually measure for very dim sources. And in the combination of the photometer and photomultiplier tube was used in combination with photographic plates for many years to do much of astronomy. The next big invention, and a quite revolutionary one at that, was the invention of the charge-coupled device. So this was done in 1969 by Willard Boyle and George Smith at Bell Labs. And as opposed to the photoelectric sensors from before, these use what was known as the photovoltaic effect. And so instead of fully ionizing the electron and having it just kind of be free out in the device, the electron is instead promoted from what we call the valence band, so where it normally kind of sits in the semiconductor, up into this conduction band. And while in the conduction band, the semiconductor, hence its name, acts like a conductor, and these electrons are able to flow as they would like in a metal, but still be contained within the material. And it just so happens that for silicon, this gap is in the optical wavelengths. And so using this, well, you can have a photon that comes in, promotes an electron up into the conduction band, and you can then collect that and measure it. And so the CCD operates just like this. You have photons that come in and generate these photoelectrons inside of the bulk material. They're then captured in this potential well here, this white area, and it's created by applying a potential to the top part of the CCD. And then you need to actually read out this charge. And to do that, you can change this potential and essentially shuffle this charge across the detector into the far corner where you have some way of reading out the charge. This is what we call the bucket brigade model, where you can essentially think of it as a bunch of people standing out in the field with buckets while it rains. And when it's done raining, the first guy dumps a bucket over to this guy who will weigh it and tell you how much there is. And then the guy beside them transfers it over like a conveyor. And then he again dumps the next one over, and then they weigh it. And so you are able to read out the charge of every single one of these pixels, but you just have to wait for the charge to migrate all the way down and over to be read out at the very end. As a side note, the charge coupled device was awarded the Nobel Prize in Physics in 2009. And then this other guy did work on fiber optics, and they shared the Nobel Prize with him. So, in 1973, only 4 years after the invention of the CCD, astronomers very quickly realized that this was hugely applicable to astronomy. And Jim Janicek from JPL and Brad Smith from our very own University of Arizona went up to the 61-inch telescope on Mount Bigelow and took the first scientific astronomical images with the CCD. This is not that image. This is an image of the moon from an amateur astronomer from earlier that same year. However, this is that image. And before I tell you what it is, I want you guys to try to guess what this object is. Yes?
Mars.
It is not Mars. I saw a hand in the back. This is Uranus. So this was the first image of us using a CCD of an astronomical object that was published in a paper and used to do actual scientific research. The reason they wanted to look at Uranus, they also looked at all of these objects, but the reason they specifically wanted to look at Uranus was because the Voyager probes had been proposed and were going to then take images and characterize Uranus. And they wanted to measure the radius of Uranus before Voyager got there. And so this image was used to do the first measurement of the radius of Uranus. CCDs very quickly took over in astronomy. You had the best of both worlds from intensifier tubes, photomultiplier tubes, and photographic plates. You could get these actual two-dimensional images that had the quantitative linear response of intensifier tubes across the whole regime. And so you can see here, even in 1994, CCDs accounted for essentially 100% of the detectors that were being used for astronomical purposes. I do want to point out, however, that some science is still done with these other detectors. Specifically, photomultiplier tubes are still used in the X-ray and gamma ray because of the mechanism of production and how those detect light. Photographic plates, while not currently in use for taking new data, are still of importance to archival surveys that are looking back at decades and decades and hundreds of years of data to then compare to newer data to get a picture of things that evolve over longer than human lifespans. The first CCD was sent to space that we know of in 1986 aboard the ESA's Giotto mission on the Halley multicolor camera. This spaceship flew two 390 by 292 pixel CCDs, and here you can see one of the images they took of Halley's Comet. Now, this wasn't the first detector sent into space. Those would be photometers, but this was the first time a CCD was flown in space. And of course, ever since then, they have been the choice of detector for optical wavelengths. This mission, I will also point out, was a massive failure. It went offline about half an hour before coming into close orbit of Halley's Comet, and so there was zero data of the actual surface of Halley's Comet. The next big invention for astronomical detectors is the complementary metal oxide semiconductor detector, or CMOS, as you may know them. This was invented in 1992 by Eric Fossum at JPL. And as opposed to the CCD, where you have to wait for all of the charge to be read out and transferred to the other corner, all of the electronics are self-contained in each pixel. And so there's no waiting. No waiting to transfer the charges. These are the devices that are in your phones and in most commercial cameras. They're faster than CCDs, but having all of these electronics right by where your charge is stored and collected does introduce more noise and more opportunities for things to go wrong. You may also notice, unlike the CCD, the entire pixel cannot collect charge. There are parts over here where if a photon strikes and an electron is generated, it will not be measured. This can be solved by things like microlenses that will focus the light into the specific part of a potential well, but they still have a lower covering fraction, the amount of space that they actually are able to image, than a CCD. So as for what is happening currently with astronomical detectors, specifically in the optics, the next frontier is the photon counting frontier. We want to be able to individually count every photon that strikes our detector. And as of right now, most detectors, CCD specifically, are able to capture and generate a photoelectron from every photon, but we are limited in how accurately we can measure the number of electrons in each pixel. And so there are several solutions that have been proposed and developed, electron multiplying CCDs, skipper CCDs, and then in general, these regimes of quantized CCDs and quantized CMOSs that are just devices that are able to do photon counting. And so I work on skipper CCDs. These were originally hypothesized and theorized in 1990 by Jim Janisic, also at JPL, but they weren't first fabricated successfully until 2017. And unlike a traditional CCD, where the guy weighs the amount of water, you measure the amount of charge in each pixel just once, you can do this numerous times. And as you do this, you can average the charge every time and average out some of the noise that is generated when you measure the charge. I won't go into the details of this diagram, but this here, T1 to T2, you can flop the charge on and off of where you're measuring to get multiple independent measurements of the exact same charge. So a little bit more about my research. I must say I'm a slight bit of a traitor because I don't work in the optical. I actually work in the ultraviolet. However, the principles are all the exact same. And so, here you can see one of our setups we're designing to mount these CCDs and actually measure their response to light and how accurately they're able to measure charge. And then here is the full setup. We have to operate in a vacuum because we're doing ultraviolet. And then we have to be able to cool the detector as well. I also wanted to go ahead and share some data we have taken with these skipper CCDs. And on the spot on the right here, what you can see is the amount of noise on the y-axis versus how many times we are reading out the sample on the x-axis. And this dashed black line is the theoretical square root of the number of samples reduction that you would think. And what you'll see is that up until about 1,000 samples, it follows this perfectly, where you hit what is essentially a noise floor, where now the noise you are seeing is no longer generated by sources that can be averaged out by taking multiple samples. And on the right, this is just a raw signal that we get from the detector itself. So what's next for the future of astronomical detectors, optical detectors, etc.? Well, it's what we like to call the perfect detector. In my research for this talk, I found notes of the perfect detector going back as far as like 1992. And so, people have been saying this is right around the corner for decades now. But ideally, the perfect detector would count every single incident photon without missing any, without any losses, without any noise. Additionally, it would encode not only the time position for when the photon arrived, but also the energy of that photon. And then also would have things like, requiring low power and low thermal loads. In the optical, there are not many great solutions for this, specifically because the way we detect light with like CCDs is not conducive to encoding time and energy. But in other wavelengths, there are lots of solutions that are being developed currently that have the possibility of being this new perfect detector. So as I leave you here, I want to look up this timeline of all of these things we just talked about, and I will go ahead and take questions now. Yes.
Sorry, did you say you do infrared?
So no, I said I do ultraviolet.
So why is it that you have to do this?
So why the question was, why do you have to do ultraviolet in a vacuum? Ultraviolet light, especially at the shorter wavelengths, higher energy, is absorbed by the atmosphere. And so you have to get rid of all the atmosphere so you can actually have your light, make it from one side of your device to the other, make it through your setup or system or whatever. Yes. This is a great question. So he's asking, we're making these CCDs, where are they going, what are they on, etc. So the proposal, what we tell NASA is that we want to put these on the Habitable World Observatory. And so that's NASA's next big flagship mission. And they are currently going through, initial designs and concepts for this, where we need these ultra low noise detectors. And so that is the end goal of developing these, is getting them on something like habitable worlds. However, there are things that are more in the future, or more near in the future than habitable worlds. And so we do everything in space because we have to through the ultraviolet. And so there is a couple missions that we have proposed to send up either like a small spacecraft, CubeSat, or balloon-based spectrographs, where Skipper CCDs would be an ideal candidate. And then there's also use for these in ground-based instruments, because you have this really low noise, you can count photons. Things like spectrographs, you can spread out the light even more and get really, really high wavelength resolution. And specifically, Skipper CCDs operate functionally the same as a regular CCD. So anywhere that you have a regular CCD where you don't need to operate fast like a CMOS, you can slide in a Skipper CCD and see improvements in signal to noise ratios. Yeah.
So, like some detectors sometimes so what makes it so unoptimal?
So the question was, X-ray detectors have been counting individual photons basically forever. What makes it so hard in other wavelengths? So I did not look up how most of the modern X-ray detectors actually work. But generally, they have some way of measuring the charge or current just throughout time. So instead of like collecting all of the photons, they measure the pulses usually that come in from the photons, and you can see the response. And so you can count how many pulses, how many incoming photons you have. Because of how we detect them in the optical, we don't do the same as we do like in the X-ray or other wavelengths. Resolving them with time would require a completely new detector architecture. The way that we have them stored in these potential wells in a CCD, you lose all of the time information. There are things that are being worked on that could do things like this. And so I don't remember what the acronym means, but there's SNSPDs, which are essentially thin wires that have some quantum interaction with the photon. And then if you know that you interact with this wire and this wire, you then know where it interacted on the detector. And then you can measure each wire's signal over time and get a time-resolved image. But those things are still being worked on. They don't have the same image detection efficiency that like a traditional CCD has. And so those are one of the options for, this possible future, perfect detector. But at least for right now, they are not as good, not as reliable as a traditional optical detector. Yeah. Yes. Okay, so the question was, in our diagram, we showed that we had a cryocooler. How important is that for the thing operating properly? And the answer is that it isn't necessary for the operation of the CCD, but it is necessary for the properties we want to observe. And so when you have an object that has a temperature, there is a chance that thermal electrons can be, or electrons can be thermally excited from the valence band to the conduction band just based on the energy that's contained in each particle. And so what you get is that at warmer temperatures, you have lots of these electrons that are being promoted into the valence band, and you get lots of essentially a false measurement, a false signal, where you're not actually receiving any light from the object, but you measure light in your detector because of all these electrons that are being promoted from thermal effects. And so by cooling the detector, we can reduce the number of thermally generated electrons exponentially by the temperature. And so we cool to about minus 100 Celsius for where we want to operate with the dark current we want to measure. Yes.
So, like a normal CCD image, you know, kind of get like you can. I assume you could judge the number of photons basically by how, and you know, you can if it's saturated, you could change the exposure or something. So why is it important to give?
So the question is basically, why is it important for us to be able to count individual photons when CCDs can still get the number of photons just from how bright the source is? And so the answer is when we're measuring really, really faint things that only produce a few photons, you know, per minute, per hour, per second, or whatever. If we're only able to measure, you know, say 5 electrons or 5 photons from the object, we may be missing out on important science that can be done in that really, really faint regime. And so it's not necessarily that we need to be able to count all 60,000 photons that come from an object, but if we only get 5 photons from an object, we really need to make sure we count all of those and we don't lose any. You know, because even if we lose 1 photon of 5, that is a 20% reduction in signal, and that can have drastic implications for the science we're trying to do. One more question. Yes.
Which astrophysical source
So the question was, which astrophysical sources am I most interested in collecting photons from? So for our research in the ultraviolet, we are looking at the circumgalactic medium. And so that is the diffuse gas and dust around galaxies, but not in between galaxies. It's the gas and dust that is still gravitationally bound to the galaxy. This gas is incredibly diffuse, producing, you know, just a few photons per hour for us to detect. And so in the nearby universe, all of this is produced in the ultraviolet. Hence why we want to look at ultraviolet wavelengths. This has been done in, you know, the farther away universe where photons are redshifted into like optical wavelengths, and you have the sensitivity you need. But in the ultraviolet, in the nearby universe, we want to know how the circumgalactic medium forms, how it evolves, what its distribution is. Right now, there have been no missions that like map out the circumgalactic medium in a mission around nearby galaxies. And so we're interested in looking at, you know, how all these metals come in and out of the galaxy because they have to pass through circumgalactic medium, and what effects this has on galactic evolution.
All right, and that will conclude Space Draft 113. Thank you so much to our speakers today, and thank you all for being here. Long here in Tucson, our next show will be on February 18th, so mark your calendars. It will be here, same time, and here at the same place. To our trivia winners, please come talk to us at the merch table real quick to get your prizes. And with that, February 18th, we will see you then. Thank you all for coming.